welcome back, guys. Thank you for joining us today. JJ and I are, again, I'm Wakas Saeed.
JJ Plank.
And we're going to be looking at microwave optics. Now, this equipment looks pretty cool. And, the sound of microwave optics, I mean, when I heard microwave first, I think of, that thing in my kitchen, he reheats my food. This does not reheat my food, but it is a good demo to show how waves work. And you can think of microwave optics as a blown up version of light optics. We're looking at everything at like a much bigger scale. For example, I'm going to jump into it real quick. Like for a diffraction slit for light, we're doing another demo and we were looking at 600 slits per millimeter. Whereas like for diffraction for this, we're looking at these two slits and they're like, 5-6 centimeters apart.
Yeah. So, it takes optics wavelengths of light that were, really small, and now it's much bigger. In fact, it's the size of a microwave, right? So the wavelength is about 3 centimeters, 2-point-something centimeters.
Right. And this particular, so we have two pieces. These are our key pieces here. This is our transmitter and a receiver. So the transmitter is what's creating the wave. The receiver is what's picking it up. Transmitter transmits, the wave is about 10.5 gigahertz. And it's only about 15 milliwatts, so it's not a strong wave, but it's there. And then everything we're doing, we're setting transmitter receiver. It's somewhere between, like up to about a meter apart. So, they're not too far apart, but it's strong enough to pick up the signals at about 1 meter.
Yeah, and the transmitter and receiver, they're not overly complicated. It just uses diodes, right? So one uses a gun diode, the other uses a Schottky diode, and creates microwaves linearly polarized, right, in the direction that the diode is physically oriented in, right? And then it's receiving them using a diode, again, linearly polarized in the direction that the diode is physically in. So we're creating them here, we're receiving them here, and the polarization plane that they lie in sits in the same plane that the diode itself sits in.
And what's very important is that in order to get the correct reading, or at least the strength of the wave, like the full strength of the wave, these need to be oriented at the same angle. And it's a little bit hard to turn right now, but you'll see one is a little, one orientation that sits a little bit wider, one that sits a little bit taller. And I can easily rotate these. We have a degree indicator on the back, so I know what angle I've turned this. We're going to start off with both of these at 0 degrees. Then at 0 degrees, like my unit here has an LED at the top. That's where it's oriented correctly. And on the receiver, we have the meter oriented on the side. So it's very convenient for you guys to see. For us, we'll have to peek our heads over and take a look at what the reading is. And what's important is, so the wave, there's a slit in here that's like, the slit is like this, but the wave is actually traveling up and down like this.
Right. Yeah, and there's inside each of these is a resonator, so there's a resonant cavity in there that diode sits in, and these horns are just waveguides for those microwaves. And so we point them at each other, and one sends the wave, one receives it, and although the diode is sitting about back in here, and then the same thing with this one, the effective point at which it's being received, because of the geometry and the waveguide and the resonator, the resonant cavity in there, it's about 5 centimeters from the front of the horn here. Right?
From the front of the horn.
Yeah, and so when we make measurements, we can say, hey, this wave is being generated here, and it's being received here, right?
So, a really quick setup, so the first, so the manual that comes with the experiment, it has, I believe, 12 experiments that are included with this. So this can do a lot for just ordering one equipment set. The basic system comes with what you see here, the receiver, the transmitter, some like a reflecting lens, polarizers. It comes with a few of these things. If you buy the advanced kit, you'll get this unit for Bragg diffraction.
Yeah, it's basically an optics system. So if you had like an optics bench that had things like mirrors and diffraction slits and stuff like that, prisms, this has that, but it's just feels and looks a little different because it's on such a different scale.
Yeah, the prism for this is actually this styrofoam, prism shaped object here, which we filled with pellets of polystyrene.
Yep, styrene pellets.
Yeah.
Yep.
So this is a lot bigger than your prism for optics, but the experiment is very, very similar.
I mean, we've got this is masonite, right, with a melamine cap on it, and it's a partial reflector, right? So when we put this here, some of the microwaves are reflected and some of them are transmitted, right? So we can do experiments that have to do with refraction, right? Or we can do things like Brewster's angle if we want to figure out what.
Or the Michelson interferometer.
Yep, or we can use the Michelson interferometer. We can configure this to be an interferometer, right? Just like we saw in yesterday's demonstration, except instead of laser light, we're using microwaves.
Awesome. So let's jump into the first experiment just to show you like a really quick example or demo of how this works. So what we're going to do is we're going to set these two about 40 centimeters apart from at these points.
At the diodes, yeah.
So it doesn't have to be exactly 40, but
And so in the manual, in all of the experiments, it recommends sort of a calibration procedure. It's not technically a calibration, but you set them to 40 centimeters, and then you adjust the settings here. So there's a gain setting on the front of this receiver here, and it's got a 1x, 3x, 10x, and 30x setting, as well as an adjustable gain here. And so you move them apart 40 centimeters, you adjust this gain setting, and then you adjust this line to set it to 1 milliamp on the scale here. And so there's an analog meter, ammeter here. You set it to 1, and then you start your experiments. So you've basically calibrated the system to be, to give you measurements that are readable.
So for the first experiment, it outlines, as JJ mentioned, we're going to set it to about 40 centimeters, and we're going to just take measurements at every 10 centimeters. We're going to take a measurement of the meter reading and the distance. Now, what's important is there's really 3 readings that we're going to be doing consistently on these. It's going to be 3, 4. It's number 1 is the angle, so the angle at which these two are to each other. The second one is the distance, how far apart they are. Third one's going to be the angle of the transmitter, and then the angle of the receiver.
Right.
So did I miss anything?
No, so they're polarized, right? So the microwaves that are coming out of the transmitter are linearly polarized, right? And so if the receiver is at an angle, tilted at an angle that's not along that polarization axis, then your measurements are going to go down. And so if it's set to 1 here, if you just twist that one, you'll see that the reading goes down. And when they're at 90 degrees to each other, it's 0, right? And so when we talk about that angle in between them, right, there is a graduated angle scale on the back of each of them that we can use to measure the difference between those transmission axes.
Yeah, so the first experiment just gives you an introduction to how the system works. The second one is actually where we're doing something a little bit more creative, which is reflection. So we're looking at how waves reflect. So we're going to have a difference of angle about 45 degrees. And
you'll notice if you can see that the measurement on the analog ammeter here has gone to 0, right? Because the microwaves are going off in this direction. It's just like if you had a flashlight or a laser, right? The laser beam goes over there, we're not seeing it anymore.
So a lot of our pieces here, they're modular. We can arrange them in many different orientations. This base has a little hole in the middle, and that's to put it right dead center of our goniometer here. And it's magnetic. So, if I attach a reflector on here, it's magnetically on there. So I can go ahead and put this on here. So it says we're going to adjust these to be about 45.
Yeah, we're going to adjust the angle, so keep that, flat like that, right? And then we're going to measure, so if this is at 0, right, 180 degrees, whoops, that's 160, right? Right, you can move these and then adjust this mirror until its maximum. Mirror, I call it a mirror, right? And now we can measure the incident and the reflected angles here, right? And we can demonstrate or prove the law of reflection, right? Even though we're using microwaves instead of like a laser beam, right?
Yeah, so we're what we can do, like, let's go ahead and do the first one. Let's set this at 20-degree angle of incidence, which is 20-degree difference in angle of where the beam is coming and the reflector here. And then we can slowly rotate this and figure out where we can get the maximum reading on our receiver.
Right. So yeah, it would be 90 minus 20 is what you got right now. Right. Yeah. And so we just swing this around. You see it was maximum right about there.
Okay. And then we just go through, turn this at 20 degrees offset, 30, 40, 50, 60, and so on.
Yeah. And so for real shallow angles, right, you can have this goniometer collapse like this. And so this looks like it's about 25 or 30 degrees in terms of angle of incidence versus angle of reflection. And so we can adjust this to be maximum and then measure those angles, record them, law of reflection.
Experiment 3 in the manual is standing waves. Now, standing waves are important because you don't really think about it when you think about a wave going out, but what really happens is, when a wave leaves, it can obviously bounce off the surface and come back. So standing wave is at that point where the wave that's coming back has this, or it's changed by about half a wavelength. So the wave coming back actually interferes with the wave that's being transmitted, and at that point we call it a standing wave. So the way we can measure a standing wave is as we slide this, we'll see that the reading on the intensity, it's going to go, it's going to go up and then back down, then up and down at different points across the meter.
Yeah.
And that minimum that's a point where we're at a standing wave.
Yeah. So these resonators and waveguides actually act like a reflector to some degree. So the microwave is emitted, comes down, it's received here, but some of it gets reflected back, right? And so we get this bouncing back and forth between these waveguides of those microwaves. And the wavelength is fixed, right? And so if we can get the distance between them just right, we can set up, standing waves in between these two waveguides. And that's basically what you do. And as you adjust.
So yeah, if you take a look at the screen here, we'll go ahead and just slide one over, and you'll see.
Yeah, and so it's going up, down, up, down, up, down, and you'll see that every time it goes up and down, you're cycling in and out of that standing wave relationship, right? And so you'll see that about every half of a wavelength. So every time you move this thing, and remember it's going down and reflecting back. So every half wavelength you're cycling through. So every time you see maximum amperage to maximum amperage, the distance that you've moved is half of a wavelength, right? And we know the wavelength. And so we can demonstrate standing waves.
The next thing is refraction.
I'm sorry. And you can also do it with a reflector too, right? So these act like a partial reflector. It works, but you can use a mirror, right? Just like if we had a rope tied to a wall, except there might be a phase shift difference.
Next thing, let's look at our prism example that we talked about. In order to use that, we're going to have our, this is called a rotating table. This comes with the basic kit. It has a little notch on the bottom here, and that's so we can keep track of the angle on the goniometer. So let's go ahead and set that down. That's 0 degrees. And now for this, the angle doesn't matter, but the angle for this is really what we're looking at. And we are going to set our prism here. So the transmitter is going to send the wave to the prism. We're going to have an incident wave, which is the angle.
Yeah, so the microwaves come straight in here, right? And the medium where they're going to experience a different index of refraction is it within these pellets here, right? Oops, one just fell out. And so the microwaves come through this surface perpendicular, so it doesn't experience, right, a change in direction, but but then it hits this surface between the polystyrene and air effectively, right? And so it's going to experience a change in direction, right? And so the normal line is in this direction. We've got some incident angle, right? And so we can adjust this, right, the angle of this receiver to a position where it's maximum, so right there. And so you can see that there is a little bit of a change in angle there, right? And
so we have our angle of incidence and our angle of refraction. Refraction.
Yes. Yeah. Yep. And then we can, we can demonstrate Snell's law using microwaves.
And then the next thing we can do is polarization. Now we talked about polarization at the beginning. So the simplest way to show polarization is what JJ mentioned is by turning one of these. So actually, I'll turn the transmitter so you can still see the meter here. So as you'll see we're at pretty high value. As soon as I turn this, it's gonna go to 0. Now this is where the polarizer comes into play. Let's see what I have here.
Yeah, and so you can, just by turning the horns or turning the transmitter or the receiver, you can measure the angle there. You could do a Malice's law experiment, right? Where you can show that the strength of the intensity squared times the cosine of that angle in between them, right?
Yeah, we can actually, we can turn this, 10 degrees at a time and just get the reading of our intensity. And yeah, as JJ mentioned, use Malice's law and go about it that way. Now the other quick way to show polarization is to use the polarizer here. So we can see, so we should be getting...
yeah, so they're 90 degrees to each other, right?
Yeah.
So
they're 90 degrees, so we have no signal
yes.
that's being picked up.
That's right.
I'll put this right here with the slits this way. What's our reading?
It doesn't change, right?
Nope. So let's change it horizontal.
Yep. Still no change, right?
No change. Now here's the trick. Let's put it at 45 degrees.
Yes, now you can see that the ammeter has jumped up some, right? And so what we've got here is the microwaves come out polarized in this plane, right? And they need to be received in this plane, right? But that 90 degrees means we're not going to see any microwaves with this receiver. But as it travels through this polarizer, right, there is a component in the direction of the polarization angle of this. And so that tiny little component does get transmitted, but it's sort of projected onto that polarization, a different polarization plane, right? And then that component will be seen. There is a component of that will be seen by this. And so you can see that by adding that polarizing filter in between at some intermediate angle, that all of a sudden you're seeing light, or you're seeing the microwaves. And the same thing would happen with, light optics.
And we can also do this with, the experiment comes with 2 polarizers, so we can actually have one at, let's say like 22.5 degrees and the other one at around 66
sure.
degrees, and show the same thing that way. The second one's being in there.
Yeah, and also you can demonstrate how Polaroids or polarizing filters work, right? So you've got this. So the waves are polarized. They make it through this because that axis, that polarization axis, is the same as the transmission axis for this polarizing filter. But as soon as you put one in there that's perpendicular to it, now it doesn't make it through, right? So you can demonstrate how polarizers work.
We can also do interference with this. So double slit interference. As we showed at the beginning, this is our double slit apparatus here that we created. The experiment will tell you to try to set these about 1.5 centimeters apart. So you want to try to be as exact as we can. Let me go ahead and...
Yeah, because when the slit width is on the order of the wavelength, things start happening. Yeah.
So as we learned in the polarization experiment, the waves are actually traveling this way. So we need to rotate these 90 degrees so that they'll actually make it through our double slit or slits that we created.
Yeah, and so you can then, I'm going to move some of this stuff out of the way.
So this part will be hard. You'll kind of have to take our word for it just because of the camera angle.
Yeah, so then I can move this, I can swing this receiver around, and the amperage, the ammeter that's being read here, goes up right here where a 0th order maxima would be.
And when he says it goes up, I mean, we're talking like 0.4
it's small.
milliamps. Like it's a small change.
But then if I keep swinging it, I'll find another area right here where that reading on the scale here goes up again, right?
And
so
again, we notate that same angle and
yeah,
do it the third time.
So we could have a 1st order maxima, and then we keep going way out here, and there's actually a 2nd order maxima out here, and then we can use that relationship, right? That right.
Yeah, we can record the intensity, record the angles as we sweep across this point.
Yeah, the
make
spacing.
a nice graph, and we have our diffraction pattern.
Lambda equals a sine theta.
Lloyd's mirror. This one's kind of cool. So what this one is we're going to set the receiver and transmitter pretty far apart. It's saying at least about 1 meter apart, and normally we would use our extra track right here. Let me see if I can actually set this up. But essentially what we're doing is so we know that when the wave leaves our transmitter, it's not just going straight to the receiver. There are waves that are being propagated outwards as well. So what Lloyd's mirror is we're actually taking a reflector and we're going to be moving it towards the wave here. And actually what we'll see that the intensity will increase. It'll fluctuate a little bit, but it will change based off of the position of the mirror.
Yeah, because when that distance is just right, you get reflection back, away from the transmitter, back towards the receiver, so you get this sort of constructive interference right here.
So that's another, so we can, as we change this distance, we can, notate what the intensity is and get a nice graph that way. Next.
We have a question, guys.
Yeah.
What would happen if you place the third polarizer between the two cross ones at a 45 degree angle?
So the idea is that you would see the same thing that we saw earlier when we put the 2 horns at 90 degrees and put one in at 45. Right, that same thing would happen. The problem is you lose a lot of intensity by doing that. So it would be difficult to detect it. But yes, that you should be able to see the same phenomena. But we tried that earlier, and it was difficult to see it. It was much more dramatic when we just used the horns in a single filter at 45 degrees.
And the more plates we add in between, the more of the signal we're losing.
Yeah.
So the next step, Fabry-Perot interferometer. So with that, we can use the 2 the partial reflectors, and place them here. We can adjust the distance in between, and just to figure out where we're getting the maximum intensity. As well as after that, we're looking at the Michelson interferometer. That one, it does take a little bit of time to set up, so we're gonna skip over that part today. But it's a similar thing to the laser interferometer or Michelson interferometer that you saw, where we're using the partial reflector in the middle. It's putting some waves in this direction, some waves in this direction, and the waves are bouncing back and forth. We're going to be picking up the intensity on one side of it and reflecting on another. We're going to be adjusting that point.
Yeah, and as you adjust so you got microwaves. So this is the transmitter. The microwaves that come down. This will be at 90 degrees, right? So over here, you've got a mirror. So one of these silver pieces over here, and then a partial reflector in between. This acts like a beam splitter, right? We send some down this path, right? We send some down this path, and as they collect, they meet down here by the receiver. Depending on the position or the path length difference, you'll get constructive or destructive interference at the receiver. So as you adjust it, you'll see that the meter sort of fluctuate just as you would with our regular interferometer.
So JJ, what's this cool thing over here? This bag
Oh,
full
yeah,
of
right.
plastic pellets.
So the prism was filled with those styrene pellets, right? And so one other activity that you can do is the system comes with these bags, these long bags here. You can fill them with the pellets and create a fiber optic cable, basically. And so now we can take this and, you know, bend it to some angle, like that, let's say. And so if you here, slide this one back just a little bit. There, that's perfect. Too much. So if you hold this end of the cable, go ahead.
Yeah.
Hold it into the light, the beam of light. You can guide it back over here. You can see as I move the fiber optic cable into the receiver, you get a reading. If I take it out, it goes to 0. And so you can demonstrate fiber optics with this using these styrene pellets in this bag. It's pretty awesome.
And even when they're facing each other, we can put our fiber optic cable in between to see how it will actually help the wave. Like if I don't have, let's change our scale. I'll actually take that back. Maybe it didn't help the wave.
Well,
They've gotten that far wrong.
So fiber optics, right? You can talk about total internal reflection, right? Those microwaves go into the cable, this cable, and they stay in the cable as long as you don't bend it too much, right? So you can demonstrate. This bag's a little too full, right? If I bent it even more, I think it would probably rip. But you can demonstrate, you know, these microwaves can make it around corners by using a fiber optic cable just like this. So without the cable there, you get nothing. With the cable there, you get a reading.
So all of these can be done with the basic system as it comes with. We do have a few optional accessories that you can buy. The first is this microwave probe. What this allows, you can actually connect this to the receiver and put it in place of the receiver as like an antenna for receiving signals.
Yeah, this microwave probe connects to the receiver here, straight into the bottom, right? And so you can use this thing to probe different areas to measure the strength of those waves or the intensity of those waves. And then the same analog meter will measure those for you. So we're railed here. Turn that down just a little bit. And so if you want to explore nodes and antinodes in a standing wave, right, you can take that standing wave experiment, set it up so you've got standing waves, and then you can slide the probe through here, right? And so some of the waves are being measured, right? The strength of those waves is being measured with this diode, and some of them are making it through and still reflecting. And so you can find the areas where you've got maximum amplitude versus zero amplitude, right? Nodes and antinodes.
Now with another accessory kit that we have is it comes with this polyethylene panel here, as well as the Bragg diffraction unit here.
Crystallography.
Right. So this is similar to like what our prism was made out of. You know, it's made out of plastic that's adjusting what happens with the wave. It doesn't completely block it, but it does allow some of the wave to go through. We can actually put this on our bench here, and this is where we need that meter on there, because what we're going to do is we're going to adjust the angle between angle of incidence and angle of refraction between our panel here and the receiver, and you know, doing the same thing. We're sweeping across and looking for minimums and maxima across as we adjust the angle. But what's important here is that we need to adjust, for this experiment, we actually need to adjust the angle of both of these. So for every 1 degree I adjust this, I need to adjust this 2 degrees, because we want that angle to be similar. We want the change in angle to be similar relative to both. And then the last experiment is Bragg diffraction. Is where we're using actually this unit here. What Bragg diffraction is you'll see these metal balls that are inside of this this unit here, and what this does is it changes where the wave is reflecting. So it's depending on the angle, the waves are going to hit each one of these at a different point, and it's going to change the amount of the wave that it allows to transmit through.
Yeah, you get, it's like a crystallography, sort of a crystal diffraction pattern, right? So we can use the transmitter and swing it around to different angles, and we can measure, right, what those, we can basically detect what that diffraction pattern looks like.
So, I mean, you get the basic pattern here is, I mean, this thing is pretty all-encompassing. There's a lot of experiments it can do. This isn't just for, you know, for one day of physics. I mean, this is at least like a few days in the lab, especially when, you know, students are recording data, they're analyzing the data, they have to make the charts. I mean, there's a lot of homework to be done here. And it's cool. I mean, you can decide what you want to do with the optics. You can design the kit to however you want to use it in your classroom. And it's a much, sometimes it's a much easier way for students to grasp the idea in their mind of like a wavelength, because by adjusting this, you know, 2 or 3 centimeters, we can see the wave change versus like adjusting a micrometer on a little handle and trying to figure that out with light. But we actually will be doing something like that next, but you know, jump into that. But yeah, are there any questions from the audience on any of our on what we've shown you today?
We did get a comment if you could briefly show a standing wave
Sure.
can be measured using a reflector.
Sure, sure.
Put that in the center. Better?
Yeah, that's fine. Here, you be the probe man.
So just take a look at the intensity meter here as I go ahead and
Sorry,
I need to change.
hold it still.
I need to change the 30ths.
Oh. There. So go ahead and move closer. It goes. You can see.
So as I'm sliding this, you'll see the wave.
Go way up, way down, way up, way down, way up, way down, and you'll see the difference between one high amplitude spot and another one is half of a wavelength.
And the proper way to do it is actually use 2 of these. It's a little more. There you go. So yeah, we can just slide this back and forth, and then yeah, we'll see the intensity change on there.
Okay. Yeah.
Just back a little bit.
Yeah.
There we go.
Now move that.
There you go. There's a maxima. Right there. There's a minimum right there. So that's the point where we have a standing wave. And as I sweep across, go another about 1.75 centimeters at another maxima, and as I go again, there we go.
Yeah.
Another standing wave. Any other question?
Oh, they're asking if the sensor is included in the standard kit.
This one is not. This is an optional accessory.
And that the diode that's used in this probe, it's highly sensitive to electrostatics. So if you do get it, be very careful. You know, have students mind what they're touching. The sensitive area is that diode right in the center of it there. Otherwise, you know, handling it out here in the semiconductor is not a big deal.
All right. Well, if that's it, then thank you again for joining us. We have one more experiment that's going to happen after this. We're looking at the wireless diffraction scanner. So we'll be back shortly to show you that. Thanks.